Hello, I am Sunita. Welcome to my class. Here I am going to discuss JPSTR science topics according to the syllabus. Here the topic is magnetism. In this one we will study about solenoid, toroid and cyclotron in detail. Let us discuss in detail solenoid. An insulated wire tightly wound closely in the form of a helix. An insulated wire tightly it is wound in the form of a helix, that one we will call it as a solenoid. Then solenoid it behaves like a bar magnet. All the property of bar magnet it will exhibited in solenoid. Then here how you will judge in the solenoid which one is north pole, which one is south pole. If the current, if the direction of the current, if it is in clockwise direction, that one we will call it as a south pole. If the direction of the current, if it is in anti-clockwise, that one we will consider as a north pole. Then here solenoid it will behaves like a bar magnet. Let us consider the case for a long straight solenoid. Here they are given the condition. Length of the solenoid is longer than the radius of the solenoid. The length of the solenoid is too longer compared to radius of the solenoid. Here consider this is the length of the solenoid. This is the radius of the solenoid. That one we will call it as a long solenoid. Then here you can observe here solenoid, the current it will enters inside the solenoid, then also current it will come out from the solenoid. Here dot it will indicate the current is coming out of the solenoid, into it will indicate the current is moving inside the solenoid. Then here B it is nothing but a magnetic field. Then first one, magnetic field outside the solenoid is 0. Magnetic field outside the solenoid here, here. Otherwise magnetic field outside the solenoid always it will be 0. Then second one, magnetic field inside the solenoid is uniform. Magnetic field inside the solenoid, here you can see the arrow mark. This is the B, it will indicate the magnetic field. Magnetic field inside the solenoid, it will be uniform. Then along the axis of the solenoid also, it will be uniform or it will be same. Then third one, magnetic field along the axis, it is given by mu naught Ni. Magnetic field along the axis, it will be uniform. It is given by the formula mu naught Ni, where I is the current in each turn. You know solenoid it is the wire it is wound in the form of a spring. Then current in each turn we will given, it is given by I. N is nothing but N divided by L. N, capital N, it is nothing but total turn divided by small l means total length. N it is nothing but a total number of turns. Then here in the total number of turns, how much current it will be passing in each turn, it is given by Ni. Then magnetic field along the edges, it will be off of the axis, off into mu naught into Ni. Mu naught it is a constant. That constant we will call it as a permeability. Then these points are very important. This one you have to remember. Graph of magnetic field versus x-axis on the axis of a long straight solenoid. Length of the solenoid is much greater than the radius of the solenoid. Consider here on the x-axis, consider the solenoid, length of the solenoid. Then here at the axis B, consider the magnetic field strength of a solenoid. Then here x-axis we are considering the solenoid. Then this is at the center. X it will be 0. Consider x it will be 0 at the center of the solenoid. Then here if L is the length of the solenoid, then at the positive length, at the x-axis positive, the length it will be L by 2. Then here negative axis, the length it will be minus L by 2. If you plot the value of a magnetic field, then you can observe the solenoid, the magnetic field inside the solenoid, it will be uniform. It will represent this area. Then at the edges, the magnetic field, it will become off mu naught Ni. This is indicated this dotted line. Then here inside the length of a solenoid, the magnetic field it will be mu naught Ni. Then at the edges of the solenoid, the magnetic field it will be mu naught Ni divided by 2. It will be reduced to half of the value. Then here magnetic field inside the solenoid it will be mu naught Ni, where N it will indicate the number of turns, then I is the current. Then magnetic field along the edges it will be off into mu Ni. Then here you can observe the magnetic field along the inside the solenoid, it will indicated this straight line, this portion. Then along the edges it will be reduced to off. This is the graph given by magnetic field versus x-axis on the x-axis of a long straight solenoid, where length of the solenoid it will be much more greater than the radius of the solenoid. This point is very, very important. Let us discuss toroid. A solenoid bent into a form of a closed ring, it is called as a toroid or a toroidal solenoid. If a solenoid, if it is bent in the form of a closed ring, that one we will call it as a toroid or toroidal solenoid. This is also a type of a solenoid. Here the wire is wound in the form of a spring or a circle. Then here at the one end of the wire, consider this is the arrow mark I, the current it will enters inside the wire, then it will move across the solenoid. Then at one particular point the current it will come outside. This is the point, the current it will be coming outside. Then here you can observe, the current carrying conductor it will produce as a magnetic field. Then here in the case of a toroid, we will consider three cases how the magnetic field it is produced by a current carrying this toroid. Let us discuss here. We will find magnetic field for one points in the open space interior to the toroid. This is the point P, that is the point in the open space interior to the toroid. What is the magnetic field we have to discuss. Second point inside solenoid Q. Consider any point inside the solenoid Q, then what is the magnetic field? Let us discuss here. Then third one, point in the open space exterior to the toroid. Then point in the open space that is exterior to the toroid. Then all the three cases we have to consider the magnetic field. How much magnetic field it is influenced by a current carrying conductor, otherwise how much magnetic field the current carrying conductor it will produce. Let us discuss in detail. Consider the first case for points in the open space interior to the toroid P. Consider a point P in the open space of the toroid, open space interior to the toroid. Then if you want to calculate a magnetic field generated by a current carrying solenoid, then you have to consider a circular loop. Then according to Ampere's circuit law, integral of B dot dl it will be equal to mu naught I inside. Mu naught is a permeability constant, then I is the current inside. Then here if you consider a circular loop, then the current it will be inside the solenoid. This is the direction of the current. The current it will enters in the one end of the wire, then it will move like this, then the current it will leave at the another end. Therefore the current it will be inside the solenoid. Then interior part of the toroid you will not find any current, therefore current inside I inside it will be 0. Then substitute I the value 0 in this integral, then B dot dl it will be 0, mu naught into 0, then you will get 0. Then magnetic field inside the interior part to the toroid at a point P it will be 0, because the current inside the solenoid it will be 0. If current is 0, then it will not produce any magnetic field. Then magnetic field at a point P it will be 0. Consider the third case For points in the open space exterior to the toroid, you have to consider a point R. It should be outside of the toroid. Then what is the magnetic field at the point R? Then you know, according to Ampere's circuit law, integral B dot dl, it will be equal to mu naught I inside. Then you have to consider a circular path. That circular part, it has to pass through the point R. Then you know, already you know, the current, it will enters inside the toroid. Then it will move like this. Then it will come out of the toroid at another end of the wire. Then here observe the arrow mark of the current. The current, it will come inside. The current coming inside, let us consider as cross points, otherwise into mark. Then into all these into mark, it will indicate the current, it should be coming inside. Here see the current, see the arrow mark. The current, it will be coming inside. It is represented by into mark, otherwise cross mark. Then after entering, then at back side it will move back. Then this dot, it will indicate the current, it will be going outside of the toroid. This dot, it will indicate the current going out of the toroid. These all the dots, whatever the dots I am mentioned here, these dots, it will indicate the current is moving out of the toroid. Then here observe the arrow mark. From this arrow mark, the current, it is moving inside the toroid. It is indicated by into or cross mark. Then it will move like this. Then it will go out. It is indicated by dotted. It is indicated by dot. It will indicate the current, it will be going outside. Here in this case, the net current will be 0, because how much current it will enters inside the toroid, it will be equal to the amount of current going out of the toroid. Then here consider the direction of the loop. Here in this direction, the direction of the loop, it will be in clockwise direction. You know, there are two types of current are there. One is positive current and another one is negative current. Here when you consider the direction of the loop is clockwise, then the current entering inside the toroid, it will be positive. Then the current coming out of the toroid, it will be negative. Then how much current it will enter inside the toroid, it will be equal to the amount of current coming out of the toroid. Then net current, it will be 0. Therefore here n, it will indicate the number of turns. Then how much current it will enters inside the toroid, it will be equal to the current coming out of the toroid. Therefore net current, it will be 0. Therefore integral B dot dl, it will be 0. Then magnetic field at the point R, it will be 0. Consider the second case here. For points inside the toroid, you have to calculate the magnetic field inside this toroid. This blue color, it will indicate the inside the toroid. Consider a point Q inside the toroid. Then you have to calculate a magnetic field. First, let us construct a Ampere circular loop, because if you want to calculate a magnetic field at a particular point Q, then you have to consider a circular loop. Then according to Ampere's circuit law, integral B dot dl, it will be equal to mu naught I inside. Then R is the distance between the center of the toroid to the particular point Q. Otherwise R is the radius of that particular circular loop. Don't get confused. This R is the radius of the circular loop. Then here in the case of a toroid, you can find out two circles. This is the first circle, inner circle. Then it should be the outer circle. Then inner circle radius, it will be indicated by A. Then outer circle radius, it will be indicated by B. Then here this value, this R, it will be it will be more than A and less than B. The R value, it will be more than A and less than B. Then R values is like between A and B. R is the radius of this circular loop. Then here the I is the current, amount of current it is entering inside the toroid. Then it is indicated by cross mark. Always the cross mark, it will indicate the current it is coming inside. In each case, inside the circular loop, the current it will be coming inside to the toroid. Therefore, this current let us consider as a positive. Then here inside the circular loop, we have to consider only the positive current, otherwise the current entering inside the toroid. Then here the direction of the loop, circular loop, it will be in the clockwise direction. Then if you want to calculate a magnetic field at a particular point Q, then you have to consider a small length of the toroid, otherwise small length of the wire. Here this small dl it will indicate, then here also this dl it will indicate the small portion of the length of the wire. Then here at this each point, the magnetic field is tangential to the circular loop. Here this also tangential, this also tangential, this also tangential, this also tangential. Then here, then according to this one, the current inside the toroid we will consider as a positive. Then here this Ni it will indicate, this capital N it will indicate the number of turns. We are having here N number of turns. Therefore, the total current it should be Ni, because this current we have to multiply by N, total number of turns. Then integral B dl cos 0 it will be equal to mu naught Ni. Here cos 0, the value of cos 0 it will be 1. Then here magnetic field, already we know magnetic field inside this circular loop, at if you consider at any point it should be constant. If you consider a small portion of the length of the wire dl, then magnetic field here also it is constant, here also it is constant, here also it is constant, this point also it will be constant. Therefore, magnetic field inside the circular loop it will be constant. Therefore, take B outside. Then integral dl it will be equal to mu naught Ni. Then if you join all this small part of the line segments, otherwise length of the wire dl, then it will form as a circumference of the circular loop. Otherwise each dl if you join together, then it will form a circumference of a circular loop. You know the circumference of a circle, it is nothing but 2 pi r. Therefore, in the case of a integral it is nothing but overall dl it will be equal to 2 pi r. Then it will be equal to mu naught Ni. Then magnetic field it will be equal to mu naught Ni divided by 2 pi r. This is the magnetic field at the point Q. How much magnetic field it will experience at the point B. At the point Q it will be equal to P, it will be equal to mu naught Ni divided by 2 pi r. Let us discuss next one, cyclotron. Cyclotron, it is a device used to accelerate charged particles like proton, neutron, alpha particles, etc. to very high energies or velocities. It is also called particle accelerator. Cyclotron, it is nothing but it is a device used to accelerate a charged particles like proton, neutron, alpha particles. Here you have to remember, it will not accelerate electrons, except electron. It will accelerate almost all the charged particles. And here if it is accelerate, then that charged particles it will move with high energies or high velocity. Therefore, cyclotron we will call it as a particle accelerator, because the cyclotron, the device function itself is it will accelerate the charged particles. Then here next question, how you make an charged particle to accelerate continuously? Continuously it will be in accelerated position, or continuously it will be with high velocity with high energies. If you used a electric field, then electric field it will apply say force to a particular charged particles, and because of the electric field continuously applied on a charged particles, then charged particles continuously it is getting energy, and velocity of the charged particle it will be increasing continuously. Then here if you apply a electric field to a particular direction, then the charged particle it will move in the same direction only. Then if you want to keep a charged particle continuously in accelerated position, then in the same direction, in same way you have to apply a particular electric field. But you can't keep the charged particles to a longer distance. Then you have to make an arrangement like that. You have to apply a electric field to a particular charged particles because it has to increase its velocity. Then you have to make that charged particle to change its direction continuously after traveling some distance. This is done by making it pass through a limited width of electric field a number of times. Then you have to create an electric field with a limited width of electric field a number of times. Then here, if you want to change the direction of a charged particles, you have to apply a magnetic field. If you only use an electric field, it continuously apply a force on a charged particle, then charged particles, they will get accelerated. But if you want to change the direction of an charged particles, you have to use a magnetic field. This can be done with the help of a perpendicular magnetic field B, which rotate the charge a number of times in the electric field. If you apply a magnetic field perpendicular to the direction of electric field, then that particular charged particle, it will acquire a force or moving with high velocity, otherwise it will get accelerated, and after some distance, after covering its particular width, then it will change the direction. Even though it is changing the direction, then that acceleration of the charged particle, it will not vary, it will be accelerated always. Let us discuss in detail working of a cyclotron. Cyclotron, it contains two Ds, D1 and D2. D1 and D2 are hollow semi-cylindrical conductors. Then here you can observe, this is the Q is the proton source. Then these two dies, it kept inside a vacuum chamber. Then here this into mark, it will indicate magnetic field into the plane of a paper. Then this one HF oscillator. HF oscillator is nothing but high frequency oscillator. This oscillator, it will help to change the direction of an electric field. Then here two important point you have to remember. When proton enters inside the hollow semi-cylindrical conductor, then electric field, it will be zero. Then it will experience only the magnetic field. Because of the magnetic field, it will change its direction. Let us study in detail. This Q is the source of the proton. When proton released from the source, then it will move towards the D1. D1 means hollow semi-cylindrical conductor. It will move towards D1. This is the direction of an electric field. Then when it is reached D1, inside hollow semi-cylindrical conductor, electric field is zero. It will experience only the magnetic field. Therefore, because of the magnetic field, the proton, it will change the direction. From this is the direction of an electric field. Because of the zero electric field, it will experience only the magnetic field. Therefore, the proton, it will change its direction. This is the first case. Consider this is the first case. In this case, this is the direction of an electric field. Then when it is reached the D2, then again the direction of an electric field, it will change. Before it is this is the direction of an electric field. When it is reached D2, then this is the direction of an electric field. This change in the direction of electric field, it will happens because magnetic field is applied on a particular proton. Because of the magnetic field, the direction of an proton, it will change. When it is reaches D2 hollow semi-cylindrical, again at this point, the electric field, it will be zero. Then it will experience only the magnetic field. At this case also, the direction of a proton, again it will change. Then you can observe each and every time the radius of the circle, it will be go on increasing, because the proton each and every time it will change its direction because of the magnetic field. Then when it is changing direction, it will gains the velocity. Because of the high velocity, then it will covers more distance. Because of the more distance, the radius of the circle, it will be go on increasing. Here two important point you have to remember. When the proton, when it is reaches to hollow semi-cylindrical conductor, then inside the semi-cylindrical conductor, electric field, it will be zero. It will experience only the magnetic field. Because of the magnetic field, it will change its direction. These 2 points are very important. Then when it is reached at this point, target, assume if the target is negative potential, then this is attracted by the proton, then it will come and it will reach this target. Then let us see frequency of oscillator. It will be equal to frequency of charge. Here high frequency oscillator. What is the help of high frequency oscillator? It will change the direction of an electric field. Then F, it will be equal to 1 by T. It will be equal to 1 divided by 2 pi m divided by QB. Then F, it will be equal to QB divided by 2 pi m. This is the potential of an oscillator, high frequency oscillator. This much frequency you have to apply in the case of a cyclotron. Let us discuss limitation of cyclotron. It cannot be used to accelerate neutral particles like neutron. It can't be used to accelerate a neutron. Neutron is a neutral. It is not a charged particle. Therefore, it is not applicable for neutron. Then second one, it cannot be used to accelerate electron. This cyclotron, it is not used to accelerate electron. Let us see why. Because of the small particles like electrons, mass vary with high speed and mass increases. If velocity of the electron, if it is increases, then mass of the electrons, it will be vary. Then when mass varies, it will affect on the frequency of an electron. Frequency, it will be equal to QB divided by 2 pi m. If mass increases, frequency also continuously it will be increases. Then you know in the cyclotron you are having high frequency oscillator. Then that oscillator also it will changes frequency. Then electron also it will be continuously, it will go on changing its frequency. Then both the frequency it will not match. Then you can't accelerate the electron because of falls out of frequency with oscillator. Both the frequency it will not match and frequency it will get falls down. Therefore, because of this condition, you can't use cyclotron to accelerate electrons. Thanks for listening my class. Send me your valuable feedback.